So there is something that I should have pointed out to you when I was giving you the preamble to Faraday's law, but it's okay because I can use it now to point out how Lenz's law works. What I was showing you, if you remember, was that if you have a coil in a magnetic field and you pull the coil out, you're going to get a current in the coil because the magnetic flux is changing. And if you bring the coil back in, you will get an EMF that will generate current in the opposite direction. And at some point during that video, I said, I showed you this, and I went like so. What I probably should have pointed out to you at the time was that what I'm actually generating right now is alternating current. Okay? And in fact, if you were to go to Hoover Dam, and if they let you into the inner sanctums, what you would find would be hundreds and hundreds and hundreds of little people down in the catacombs of Hoover Dam going like this, frantically generating the AC that you and I use every day, in our homes. That was a joke, clearly. Obviously that's not the way AC is generated with people going like this frantically. But it does turn out that if you move a coil in a magnetic field, you will generate AC. And the way they do generate AC is by moving a coil in a magnetic field. So what I want to do right now is to take a little bit of time and talk about Lenz's law, which, if you remember, is the law that allows you to determine the direction of the current flow in a coil in which there's changing magnetic flux. So I'm going to identify this side of this coil with this alligator clip so we can keep track. And what I'm going to do is I'm going to assume that there's a magnetic field that's coming from me toward you. And I am going to rotate the coil like this. And my question to you is, in what direction is the current going to flow? So this wire is such that the wire goes down and then it goes this way. So it circulates like this and then it comes out here. So the question is this going to act like the high voltage side and this the low voltage side? Or is this going to act like the high voltage side with the current flowing this way and this the low? If I go from this position to this position. So think about it. Magnetic field is coming out at you. You're going from here to here. What's going to be the direction of the current in the circuit? Is this acting like a high voltage side and this a low, or vice versa? So go ahead and pause the video, see if you can't think your way through it, and then come back. Okay, so you should be back, hopefully. And this is the reasoning that I'm hoping that you went through. So you have a magnetic field. The external magnetic field is in this direction. The magnetic flux is diminishing, which means the induced magnetic field is going to be in the same direction as the external field. To do that, the current that's going to be required to generate an induced magnetic field in that direction is going to have to flow this way. Which means in this particular instance, this is going to be the high voltage side and this is going to be the low. So just remember, this is the low voltage side when we get to this position. Okay, now we're going to go from this position to this position. In what direction is the current going to flow? Which is to say, is this going to be the high or the low voltage terminal? So go ahead and pause the video and see if you can't figure it out. Again, magnetic external field is out, like so, and you're going from here to here. See if you can figure it out. Okay, you should be back. So once again, think about the way Lenz's law works. Step number one, identify the direction of the external magnetic field. It's that way. Step number two, identify whether the flux is increasing or decreasing. It is increasing. If that's the case, the induced magnetic field is going to be opposite the external field, which means it's going to be this way. So what direction does current have to flow to get a magnetic field this way? Well, it's got to go like so, which means it's apparently entering here, so to speak, and coming out here, which means this is still the negative terminal, this is still the positive terminal. So going from here all the way to here, all of the change of fluxes that occur, according to Lenz's law, are going to end up motivating charge to move as though this were a high voltage terminal and this were a low voltage terminal. Now, once you get into this position, keep going. See if you can't do it. So I'm going to go from here to here. Use Lenz's law and see what the direction, you can kind of psych it out by just using your head, but don't do that. Actually go through the steps and see if you can't identify. Figure it out using the steps. What should be the direction of the current flow as the coil goes from here to here? Go ahead and pause and do it. Okay, so you should be back. So once again, external field is this way. Magnetic flux is decreasing, which means the induced magnetic field is going to be in the same direction as the external, which means the current's going to have to flow like that, which means current's coming in here and going out there, which means now for this motion, this is the high voltage side. So apparently, when it's like this, from here to here, this is the high voltage side. And from here to here, this will be the high voltage side. And from here to here, this will be the high voltage side. And from here to here, that will be the high voltage side. So what power plants basically do is the following. They have some way to motivate a turbine to rotate. So this is the symbol for a turbine. It could be water flowing over the turbines. It could be in a nuclear power plant, they create steam from the energy from the nuclear reaction. In coal plants, they burn coal to create steam. Somehow or other, you get a turbine rotating. The turbine is attached to a shaft, which in turn is attached to a coil that is sitting in a magnetic field. The coil's leads are attached to sliding contacts. And basically, as the coil rotates, the leads go from positive negative to negative positive, essentially generating AC. And so that's actually how AC is generated in power plants. Interestingly, in the United States, the frequency of rotation, which is to say the frequency that the turbines are constrained to rotate at, is 60 cycles per second. So the power that you got out of your wall sockets is 60 hertz, 60 cycles per second. In Europe, for whatever reason, their turbines are constrained to rotate at 50 cycles per second. So if you take, in the old days, if you had like a little radio or something that plugged into the wall, actually I don't know if a radio might not affect a radio, but if you had like a VCR in the old days, and you tried to run an American-made VCR in Europe, it would not work because the VCR actually used the line frequency in the electronics, and the line frequency in the United States is 60 cycles, and the line frequency in Europe is 50. So, anyway, that's the deal with the production of power, and it also has to do with the use of Lenz's law, or giving you some practice using Lenz's law. So.